All right, awesome. So welcome to Astronomy on Tap. Charlottesville, guys, we're going to get going in just a minute or so. And so keep chatting amongst yourselves. My wife is currently walking around with some trivia sheets. Anybody that wants to join us for trivia for tonight that's hanging out in person, we'll be passing out those trivia sheets. And we're going to get going in just about a minute or so. So I'll come back on the mic then to get us going. Thanks, everybody, for coming. And just a moment before we're going to get started. There actually is one, but I don't have it. Don't let them know. Yeah. Oh, we're doing great. Yeah. All right, hello everybody, and welcome to Astronomy on Tap Charlottesville. We're going to go ahead and get started for tonight. First things first, I want to just give yourself a round of applause for coming for tonight, joining in the process of science, welcoming you to the Astronomy on Tap Charlottesville family. For those of you guys that this is your first event, you might not know it, but AOTCville, we are a family together. You guys have joined the family. And so welcome, get close to your neighbors, get to know your neighbors. We're going to be engaging, hopefully, and discussing and one of the greatest things we can do, which is discussing that science and proceeding in the process of science. If anybody from Firefly can hear me, if you can turn the music off, that'd be great. Cool. Okay. All right. So for those of you guys that is your first Astronomy on Tap Charlottesville event, you're probably wondering why there's a grown man dressed as Buzz Lightyear in the front of the room. Many people over the years have known me as Matthew Pryl. They would say that I was a professor of astronomy at UVA, and I've been doing so since 2021. But 2 hours every other month, I become my true self. I become Professor Buzz Lightyear, and we're not going to take ourselves too seriously over the next 2 hours. But what we're going to be doing is we're going to be thinking a lot. We're going to be hearing some really cool knowledge, some cool astronomy facts, and then we're going to be playing some fun trivia as well. And so I'm going to be your MC for the night, and we're going to be leading you through some really great astronomy talks and some great trivia. We have 3 great speakers for tonight, both from the astronomy community at the NRAO, the National Radio Astronomy Observatory, and some grad students and some postdocs at the University of Virginia Astronomy Department. So a good amount of talks coming up for you. Now, Astronomy on Tap Charlottesville. Those of you guys that have been here before, can I get a round of applause? Those of you guys that have been to an AOTCville event before. Nice, okay. What about if this is your first time? Can I get a round of applause for those of you guys? Awesome, yeah, thanks for those of you guys that are coming. Astronomy on Tap Charlottesville, it's one of many satellites of the Astronomy on Tap group that sort of started taking astronomy talks and trivia to the local community about 10, 15 years ago. The Charlottesville branch was started by my good friend Trey Wenger, and myself when we were graduate students at UVA. So I was a graduate student at UVA up until 2021, and then I was able to trick the astronomy department into hiring me as a faculty member, which has been great for me, financially at the very least. And so we've been hosting those Astronomy on Tap Charlottesville events since. We're up to our 36th event, just trying to bring astronomy to the community and bring back sort of that knowledge, that fun that we've observed and we explored over the years. For the event tonight, the way that it works is that we're going to have some talks interspersed by trivia. And so we're going to have 25 minutes of talks from Chris, Ashish, and Anna. That's going to be given some talks both about the radio spectrum, how we go about making a planet, and then additionally, some of the information that we've gathered about massive stars in the universe. And interspersed between those, we're going to have some trivia, both about radio astronomy and some of the other fun things that we've explored and learned over the years. Some of the ways that you guys are going to be able to potentially win some of those prizes is by answering some of those trivia questions over the next 2 hours or so. It's going to be clear tonight, and so it's very likely that I'll be setting up my telescope after the event as well. Normally I'd set it up before the event, but since it's daylight savings time started, we can't do any observing before the event. I'll be setting it up after the event, and we'll be doing some of that as well. Halfway through, we're going to have an intermission. During that intermission would be a great time to get another drink, to get some food orders, and to chat amongst your new family members and things like that as well. I do want to point out a couple of things. First things first is we are a volunteer group. We appreciate any donations that you guys are willing to provide. This is sort of the only shill that I'll give over the course of the entire 2 hours. But any of these prizes up the front, we're going to be giving them away for free. We appreciate those of you guys that can donate to do so. And we try to have a little bit of fun with the way that we do our donations. What we're going to be doing is we're going to be choosing between our favorite radio telescopes, deciding between either the Green Bank telescope or the Very Large Array. You vote with your money up the front. So we appreciate any donations that you guys are willing to give. And then last thing that I want to note has to do with a couple of events that we have coming up. But most importantly, I want to emphasize our next Astronomy on Tap event. Typically, we have Astronomy on Tap events the first Monday of every odd-numbered month. And so the next one should be the first Monday of May. But me and my wife, I don't know if you can see her, me and my wife who hold the events, we are expecting a baby late April. And so I've been... Yeah. And so I've been told that we probably can't have an Astronomy on Tap event a week or so after that, despite my best intentions. So we're going to be trying to get back in July for our next Astronomy on Tap event. But there's a lot of great events. I'll point out some of those a little bit later in later in today's event, how you guys can continue to engage in the astronomy community going forward for March and things like that. Quick shout as well to the Charlottesville Astronomical Society. Those of you guys that like observing through telescopes, which should be every human on the planet should like observing through telescopes. If you like observing through telescopes and you want to do more of that, the Charlottesville Astronomical Society does a lot of that around the community. So I encourage you to chat with me or chat with some of the members about that. Okay, so let's go ahead and turn it over to our first speaker of the night. Our first speaker is going to be Chris Dupree from the National Radio Astronomy Observatory, or the NRAO. And so a quick round of applause as Chris comes up, and I'm going to read off some information about him. So Chris is the Assistant Director of Spectrum Management at NRAO, and he got his PhD in 1996 for massive star formation, which Anna's going to be talking about a little bit later as well. Chris specifically studied star formation, massive star formation in the Milky Way galaxy using the Very Large Array. Since then, he's done research and taught at Agnes Scott College in Atlanta, and he joined the NRAO in 2021. He's also a writer. He's published popular science books, including The Complete Idiot's Guide to Astronomy, Idiot's Guide to the Cosmos, which is great for my dad up the front is here, and all of you guys as well. And recently, Astronomical Mindfulness, and he lives in Crozet. So a round of applause for Chris as I transition over to his talks and get things set up now.
Got to get my hands straight here. Okay, can you all hear me? No. Is this on? Yeah. All right. I'm not used to using a mic. All right. Thank you for being here. Thanks very much for being here. I have lived in Charlottesville for the past almost 5 years. I taught physics and astronomy for 25 years. And actually at Agnes Scott, we have an on-campus observatory called Bradley Observatory. And we used to have big crowds, but I think booze and food probably brings in an even better crowd, right? An even larger crowd. So that's great to see. But thank you all for being here tonight. So, yeah. What I want to talk to you about tonight is the question of what is the radio spectrum and why does it need protection? And I'm going to talk to you a little bit about some of the work that I've been doing more recently since I've gotten here to Charlottesville to work with NRAO. So first of all, what is the radio spectrum? Well, it's part of, as I'm sure many of you know, because you all come to Astronomy on Tap frequently, it's part of the electromagnetic spectrum. And if you look at the spectrum there, you'll notice that there's a little tiny band of it that we're all most familiar with. That's the optical part of the spectrum. That's where our eyes evolved to see because that's close to the peak of where the sun's emission comes out of its spectrum. And actually stars are not very good radio transmitters. And radio waves start down at that very long wavelength, low frequency part of the spectrum. So if you look there, you can see they're sort of centimeters to meters, and they're down in the megahertz to gigahertz part of the spectrum. And then you move up through microwaves, the infrared, optical, and then down at the bottom part of the spectrum, I always just tell my students, you can see Incredible Hulk is there. We need those high energy radiation to make superheroes, right? So gamma rays, X-rays, those are the things that create superheroes. The part of the spectrum, the radio part of the spectrum though, is very unique in that it allows us to see parts of the universe that are impossible to see at any other wavelength. And so those very long wavelengths, they actually come right through the plane of the Milky Way very well. So my thesis work was looking at star forming regions that are in the plane of the Milky Way. If you point an optical telescope at these areas, you just see blank sky. You don't see hardly anything at all. Once you move into the infrared and then those very long wavelengths, those wavelengths come through the plane of the Milky Way, and then you can actually see some of these amazing things that are happening that are actually the very, very earliest stages of star formation. So who uses the radio spectrum? That part of the spectrum, those long wavelengths and low frequencies. The answer is pretty much everybody uses the radio spectrum. It's a very crowded part of the spectrum. And if you look at some of these pictures up there, you'll see everything from satellite imagery of weather systems, right? So very important imaging of weather systems, of our oceans. There are transmitters in all aircraft, both military and civilian aircraft. There are radio transmitters in our phones. There are radio transmitters in the wireless routers in our homes and the wireless routers in here. This wireless microphone is giving off radio waves, right? So everything is giving off radio waves. And one of the challenges for radio astronomy is that radio telescopes try to operate in that very same part of the spectrum that is not only currently crowded, but is getting more and more crowded with other types of transmitters, right? I mean, we didn't have these 20 years ago, right? All these watches that all have radio transmitters on them. We didn't all have cell phones in our pockets. We didn't have Wi-Fi transmitters in our homes, right? So this sort of steady encroachment is kind of pushing into a part of the spectrum where for a long time we were a little bit spoiled because there were big parts of the radio spectrum that weren't heavily utilized or were utilized for very particular purposes that we could kind of stay out of the way. So who uses the radio spectrum? Everybody uses it. We all use it all the time, and that's one of the things that I want to talk to you about tonight. So this is a chart that's put out by the NTIA. I'll talk a little bit about the FCC and the NTIA later, but it's a kind of mind-boggling plot that shows all of the different allocations in the spectrum in the United States. And so if you look, it starts down at very long wavelengths, very low frequencies, and it goes all the way up through the highest frequencies. And so each of those colors corresponds to an illegible key over on the left, which say things like maritime navigation or aeronautical navigation or radar or radio astronomy. And some of the little kind of bright yellow patches in there are radio astronomy. So below 100 gigahertz is where radio astronomy has some protected bands. It has below 100 gigahertz, it has a few percent at most of the spectrum is sort of protected for radio astronomy use. And that's one of the challenges too, is that radio astronomers don't build telescopes that are only sensitive to little tiny portions of the spectrum. We tend to build telescopes that have wide bandwidth receivers. And so the problem is that within those wide bandwidths, we tend to have emission that is sort of getting into our radio telescopes. So let's talk a little bit about, one more thing I want to tell you about the spectrum. So I like to think about the spectrum, the radio spectrum, the whole electromagnetic spectrum, but in my heart, the radio spectrum, because that's what we're trying to protect with spectrum management. It's a limited natural resource, right? So it's like any other limited natural resource. And so as an analogy, I just wanted to put up the various uses that might be found for a piece of land, right? So a piece of land, you could cut down lumber, you could mine it, you could let cattle range there, you could have it as a recreation area for boating, or you could have, you could go hiking. So land, no one says we should only use land for mining. Also, no one says we should only use land for hiking, right? I mean, there are multiple uses. The spectrum, similarly, is a limited natural resource, right? There's only so much spectrum, and people use the spectrum for different things. The difference between the radio spectrum and a piece of land is that it's impossible to have a piece of land that sometimes you could mine it, sometimes you could go hiking on it, sometimes you could do other things. That is one of the ways that we're trying to sort of improve the situation for radio astronomy, is to make sure that there are times when portions of the spectrum can be used only for radio astronomy. But they don't always have to be used for radio astronomy, right? I mean, radio telescopes have a variety of receivers, and you can only use one of those receivers at a time. And so if you're observing in a particular part of the spectrum, that's important. If you're in a different part of the spectrum, it's possible to have some flexibility. And so that's one of the things that we're trying to do. So I am a radio astronomer, so I do want to talk a bit about this particular use of the radio spectrum, of observing, and this is Astronomy on Tap too, so we have to talk, I want to talk about astronomy. Using the radio spectrum for astronomy, I just wanted to give an example of a very nearby source that we can use radio waves to image, and a very distant radio source that we can use radio waves to image. On the right is an image made with the Green Bank telescope that I'll say a little bit about in just a minute, located in Green Bank, West Virginia. It's actually a radar image where a radar pulse is sent out from the Green Bank telescope, strikes the surface of the moon, and then comes back and is imaged by the Very Long Baseline Array. And I'll tell you about those two telescopes in a second. So it's the Green Bank telescope, one of NRAO's telescopes, and the Very Long Baseline Array, another of NRAO's telescopes, that are used to make those images. And that has a physical resolution of about 5 meters on the surface of the moon. And then on the left is a radio image of one of my favorite sources, the galactic center. So this is the center of the Milky Way galaxy. This is an image where in the optical, you would see stuff sort of above and below the plane of the galaxy, but you would see this dark band going through the middle. And at radio frequencies, we see all sorts of emission coming off of the galactic center. And some of the things that create these radio waves, well, what created the radio waves on the right is the radar transmitter, right? It created a powerful radio pulse that got imaged. On the left, there are natural processes happening that are creating those radio waves. So this is the most technical slide of the whole night. But no equations, I don't think. Oh, there is an equation there, sorry. So I just want to talk about the two of the main ways that radio waves are created by astronomical sources. One is that charged particles spiral around magnetic field lines. And whenever a charged particle is accelerated, and moving in a curved path is a form of acceleration, that charged particle gives off radio waves, gives off electromagnetic radiation. And so if you have a magnetic field, which we often do out in space, and you have charged particles, you will create radio waves from that source. The other way you can get radio waves is if you have an ionized gas. So what that means is that, imagine a hydrogen atom, you pull the proton and the electron apart, you have an ionized gas, and if those free particles pass close to a particle that curves its path, right? An electron there is kind of moving on a curved path because it sees that proton. When that happens, you get a radio wave coming out of that source as well. So radio waves tell us about two things. One is called synchrotron radiation. That's what's coming out when you have magnetic fields. And the other is thermal radiation. That's what happens when you have a hot gas. So radio waves are big. Remember I said they're sort of centimeters to meters in size? And so as a result, radio telescopes have to be coordinately big, right? If you have big radiation, big long wavelengths, you have to have big telescopes to get nice sharp images of those big waves. And so these two here are two examples of a radio telescope. The Green Bank telescope on the left is a single dish antenna, and the Very Large Array on the right is a radio interferometer. This single dish is 105 meters across. It's the largest steerable telescope on the surface of the planet. And on the right, the Very Large Array out in Socorro, New Mexico. Its dishes are not as big. Each one of those is still pretty big, 25 meters across, but they're not as big as the GBT. But what gives it its power is that it's arranged in a shape such that the distance between the two most distant telescopes sets the resolution. So it's as if, when it's in its largest configuration, it's as if you have a telescope that's 35 kilometers across. It's not as sensitive as a telescope that's 35 kilometers across, but it makes as sharp images. Okay, so very quickly, I'm just going to show you the telescopes that are operated by, in its full name, the U.S. National Science Foundation National Radio Astronomy Observatory operates these telescopes. ALMA, which you may have heard of. Oh, why does it keep going back? Here we go. Thank you. Oops.
I think you keep clicking the bottom.
Oh, okay. I'll keep my thumb off it.
Well, I was going to blame the clicker. I was blaming the clicker.
If it insists again, we'll just go forward. Okay, we'll just go forward. The Green Bank telescope, as I told you, is located in Green Bank, West Virginia. It is basically two football fields, steerable, next to each other, can steer anywhere in the sky. It's a remarkable telescope. It's sensitive from hundreds of megahertz over 100 gigahertz. Depending on weather, it can do either lower frequency observations. The Very Large Array out in Socorro, New Mexico. I spent 2 years as a grad student out there. It's a lovely place if you ever get a chance to visit either of those telescopes. They have great visitor centers and gift shops. And the Very Large Array, shown here in its smallest configuration, each of those telescopes is 25 meters across, so bigger than this room, and they get moved around on a custom set of twin railroad tracks. So you literally unscrew some very large bolts, pick the thing up on a transporter, and then carry it out to a different pad. And it goes through those motions about every 4 months, and it goes through 4 different configurations. Even larger than the Very Large Array, not very originally named, is the Very Long Baseline Array. This is one of the telescopes. This is the one in Owens Valley in California. And pretty remarkably, these telescopes are located all the way from St. Croix all the way to Hawaii. There's a pointer in here, right? Is it the top one?
The bottom, I think.
Bottom, thank you. Yeah, so from Hawaii to St. Croix. So it's a telescope basically 2/3 the size of our planet. And those signals from each of those individual 10 telescopes get combined to form images. The Atacama Large Millimeter and Submillimeter Array, also called ALMA, is located in Chile. And this is 66 antennas that are located at a very high, very dry site. It's almost no rain. And the reason for that location is because this is a very high frequency radio telescope. So it goes from tens of gigahertz all the way up to hundreds of gigahertz, almost to a terahertz. And as a result, at those very high frequencies, telescope imaging is very, very sensitive to the presence of water vapor. And so you have to have a very, very dry site for a telescope like ALMA. Yep. Okay. I'm going to tear through these last few because I want to get to the last slides. That's just another nice image of ALMA. So quickly, I'm just going to kind of go through these because I want to end on why the radio spectrum needs protection. These are just samples from NRAO telescopes of different views of our universe. From close by, here's the sun at radio frequencies. This is an ALMA image of HL Tau, which is a protoplanetary disk forming. Pretty incredible that we are now imaging these protoplanetary disks where planetary systems are starting to coalesce out of the disks around a star. Here's a supernova remnant in Cassiopeia, beautiful freeze frame of an explosion that happened hundreds of years ago. And that, again, the Milky Way galaxy, center of the Milky Way that we saw before. This is an image by this is a magnetic field orientation, sorry. That's an optical and H-alpha image, but then the radio image actually shows us the orientation of those magnetic field lines. Remember I said that electrons spiral around field lines? You can actually get the orientation of the field lines, and we see that they line up with the spiral arms. This is an image made by another NRAO astronomer who lives here in Charlottesville, John Hibbard. When you look at a galaxy, the optical galaxy is often quite small relative to these very large arms of neutral hydrogen that kind of sweep out and cover a much larger region. And even larger are things called radio galaxies. And so in the center you have an elliptical galaxy. So this is what the galaxy would look like optically. But then radio waves reveal this enormous structure, which are these jets that are spraying far, far out beyond the size of the galaxy. Einstein predicted things called gravitational lenses. We see gravitational lenses where there are distortions in space-time caused by the mass of a foreground galaxy, and you get these very, very interesting lens structures. And then, of course, you've probably seen this very famous image, which is the event horizon around the black hole at the center of our galaxy. So, why does the radio spectrum need protection? It needs protection because I hope you agree that all of those things I just went through pretty rapidly are incredibly unique views of the universe. We can't see these things any other way. And all of these other things are competing for that same radio spectrum. So where I want to end is, how do we protect these sensitive instruments, right? How do we sort of do this thing that I'm telling you that I think we need to do? And there's many ways to do it. One is legal and regulatory structures, right? The NTIA, the FCC are the US institutions that regulate the spectrum. And the ITU, the International Telecommunications Union, meeting in Geneva right now, is the international body that nations sign on to protect the spectrum at the international level. We also create areas like the National Radio Quiet Zone, created back in 1958. You'll see Charlottesville is right here. Actually, 9th Street, I think, is the edge of the National Radio Quiet Zone. And here we have the Sugar Grove Research Station and Green Bank Telescope. This is an area where all of those technologies, at least the ones that are stationary, do have to regulate their emissions. And so they have to coordinate. If you put a cell tower anywhere within the National Radio Quiet Zone, that has to be coordinated with the FCC, and the National Radio Astronomy Observatory is sort of the front door to that coordination. So regulations, quiet zones, monitoring. We're building monitors at the NRAO to monitor the spectrum and to actually look for RFI in spectrum in areas around our observatories so that we can go and try to fix those things. Sometimes that radiation is coming, from the basement, as they say in the horror film, right? The call's coming from the basement. Sometimes we realize, like, oh wait, that's a computer we just installed. Electronics produce a lot of radiation. But oftentimes it's a cell tower that has its panel steered in the wrong direction. And then the final thing that we're working really hard on, and this is where I'll end the talk, is trying to coordinate with satellite constellation manufacturers, companies like SpaceX, Amazon, and others. And the reason we want to coordinate with them is because there are now cell towers in space. So whereas before you had your cell towers kind of around the horizon and we could sort of look up at the sky, Now we're looking at the sky, and frequently, right, every few minutes, a cell tower flies by and maybe goes through the beam of our telescope. And so we're working hard with some of these companies to try to implement a system where we tell them where we're pointed in the sky, and when their satellites come through that position that we're pointing at in the sky, they actually turn off the electronics for a couple of seconds, and then they come back on again. And this is what happens, right? So here's a spectrum. This is time on the x-axis. Here's their satellite getting closer and closer to where we're pointed, and that red part is where they actually just turn off their beamforming from that one satellite. So there are ways around this. There are ways to make multiple use of that spectrum so that commerce can proceed and the beauties of radio astronomy can survive in the modern era. And I'll stop there.
All right, awesome. So we got a couple of minutes for questions as well from Chris. And Chris, if you don't mind repeating the question as it's asked. For the first time, we're live streaming our Astronomy on Tap event. My guess is there's probably 1 billion people watching right now. And so for those billions of people, we want to allow them to be able to hear the questions as well. Does anybody have any questions for Chris? I'll come running over here.
Hi, thank you so much. So I really appreciated your commentary on the radio spectrum being a natural resource, something that can be used up. But over the past couple of days, there's been this interesting comment period on this new burst of satellites that might go up, and that includes a large, I think it's in the hundreds array of satellites, and then also separately the satellite that's supposed to quote per day and night, which is a horrible idea. So how do you see that? Because this is such a big number that they're saying that they're going to release. How do you see that intersecting with the radio astronomy's future? It's so many. I don't see how you deal with that. Thank you.
Yeah, no, the question was, with these new announcements of the orbiting data center, I think, and the reflect orbital, those are the two, how does radio astronomy survive? And it's a good question, and one of the questions is, how does any astronomy survive? Because these satellites in space, not only do they give off radiation at radio frequencies, but they also reflect sunlight. And so you have these kind of glints as satellites are kind of passing through and reflecting sunlight to the Earth. It's a huge challenge. It's, in some ways, I feel like in radio astronomy we're a little bit luckier because I think there are engineering solutions to some of these questions, because if we can successfully coordinate with these companies, and if we can kind of get in front of them and say, if you build your system in the following way, either this generation or the next generation, we can actually maybe still keep observing, there's a possibility. The challenges for infrared and optical astronomy are even greater, and I think maybe less tractable. So I don't think I have a happy answer there. The other challenge, though, is that the reflect orbital, that's where they want to reflect sunlight down to the surface of the Earth. I don't know. Sometimes I think for these enormous announcements, I have to think they won't be economically feasible and they won't actually happen, but they're just trying to get the regulatory permission to proceed. So I don't have a great answer there, other than I agree with you. If they actually launch, 100,000 satellites or 1 million satellites or whatever it is, it gets very difficult to imagine how observing on the Earth can continue. Yep.
Reflecting the sunlight seems like they're just trying to build a moon, so I take a second moon. We have a question through the live stream audience, though. One of the billions is going to ask. So.
This is a question that comes from Instagram. When we are near an observatory site and have normal or perhaps extensive RF emissions, how does it affect or react to the observations?
Great. So the question is, if you're close to a radio site and you have a device that's giving off emissions, how does that affect observing? Great question. It could be very detrimental. It depends sort of what the telescope is doing. So imagine the Green Bank telescope is observing in what we call X band, so up around 10 or 12 gigahertz. Well, if the telescope is operating there and your cell phone is using 2.4 gigahertz Wi-Fi and maybe is uplinking to a cell tower, it may not actually affect the observing that much. But if the telescope is observing at L-band, right, which is down between sort of 1 and 2 gigahertz, and you're using a phone, then actually we very much at a radio telescope would see a band of that emission. In fact, up here, I think you can kind of see it. This is actually a spectrogram taken, it's a waterfall plot taken at the VLA site. And if you look here, it's kind of hard to see, but do you see that sort of faint blue band that gets brighter here and then gets fainter again at the bottom? That is 2.4 gigahertz Wi-Fi at the VLA site. And so what that means is, and it sort of starts around 8 a.m. and ends around 5 p.m. So what that means is there is radiation coming off devices that are located at the VLA during business hours. So it does affect observing. But this is a sort of broad band coverage. This goes from 0 to 10 gigahertz. Typically, the telescope would be covering a smaller frequency range. And so the effect could be very detrimental or it wouldn't be noticed, right? And that's one of the ways that, you know, this sort of cooperation could work, right? Is that if we broadcast that we're observing at a particular frequency, and even, you know, the worst case scenario, imagine a cell tower sitting there right by the... Well, if that cell tower knows the frequency we're operating at, and it can switch to a different frequency, it could be invisible to us. So there are, that's what I'm sort of saying about to your question, there are engineering solutions possible. Doesn't mean they'll happen, but they are actually in the sphere of possibility.
We got time for one more quick question. Get up to the front, someone's got a question.
Hi, thanks. I am not an academic, I'm not a scientist, I'm just an admirer of this friend. So my question is, you mentioned gravitational lensing. Does radio astronomy play a role in cosmology? Because you mentioned gravitational lensing.
Yeah, great. So the question was referring to gravitational lensing and also is radio astronomy useful in cosmology? Absolutely. In fact, there's a period right after the Big Bang in the few 100,000 years. At about 300,000 years, there's the origin of what's called the cosmic microwave background. So that's sort of the point where radiation can first move through the universe. So it's kind of, whoops. It's kind of the earliest moment that we can see what the structure of the universe looks like, and that image is in the radio part of the spectrum. So there was a mission called Cosmic Background Explorer, COBE, and the microwave. There's another microwave anisotropy probe. So you've probably seen maybe you've seen these images that look kind of like an ellipse that have little tiny fluctuations. Those little tiny fluctuations eventually resolve themselves into the first galaxies and clusters of galaxies. So yeah, the earliest electromagnetic radiation we get from the universe it has now fallen into the radio part of the spectrum because it's been stretched out over time, over the last 14 billion years.
All right, well, let's give another round of applause for Phil for a great talk. All right, guys, what we're going to be doing now is we're going to be transitioning to our group trivia game for the night. Now, this is not going to be the ones using your sheets of paper. Instead, you're going to be using rounds of applause and sound to be voting. It's going to take me a moment to just transition to this, so get to know the people around you as I pull up the slides for our first team trivia game for tonight. All right, here we go, everybody. The team trivia game that we're going to be... some fast radio bursts coming from interstellar space right now, it sounds like. Okay, let's switch to another mic. Where'd the other one go? Hello, 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 hello. This one working? Okay. We'll see if we get any fast radio bursts from there as well. The game that we're going to be playing for tonight is something called Radio. And we're going to be having some questions that have to do with radio astronomy. See if you guys can figure out whether the answer is one choice or another. So the way this is going to work is we're going to have two connected pieces of information. One of them might have something to do with radio astronomy. The other might as well. But at the very least, one of them is going to have something to do with radio astronomy. And I'm going to ask you a question regarding that information. You're going to have to decide with consultation of the people around you whether it's one answer or the other. And the way that you're going to vote is by a round of applause, choosing one versus the other. If you guys get more questions right than wrong, at intermission, everybody can come up and grab some of these mini prizes up the front. Those of you guys that are AOT experts know that I give the mini prizes regardless of if you get more right than wrong, but it's just way more fun for everybody here if you get more right than wrong. We got 5 questions for you, but just to give you a sense of how it works. Let's imagine I asked a question like, which is larger? The world's largest single-dish radio telescope or the world's largest beer? I'll give you guys about 30 seconds to chat with your neighbors about this one and see if you can figure out which one it is. So 30 seconds to chat in here. All right, this is just our example one, so I'm not actually going to give you 30 seconds for this one. By a round of applause, who here thinks the answer to this one's the world's largest single-dish radio telescope? And who here is hoping it's the world's largest beer? Yeah, so unfortunately, it is not the world's largest beer for this one. It is the world's largest single-dish radio telescope. To put that into perspective, world's largest single-dish radio telescope, about 500 meters across. The Green Bank telescope's about 100 meters across. The world's largest beer, whoops, went back here. The world's largest beer is about 1 meter across, unfortunately. It's got some height to it, though, so a good amount of volume there. All right, 5 more questions, a little bit trickier for these ones. Which of the following happened first? That radio signals were first detected from space, or that commercial car radios began being placed in cars? I'll give you guys like 30 seconds to chat amongst yourselves for this one. All right, time's winding down for this one. Get your answers locked in. Hopefully you agree with the people around you, but if not, try to be your own person. Sometimes it's more fun to be right when everyone else is wrong. So who here thinks the answer to this one is radio signals were first detected from space? What about commercial car radios began being placed in cars? I'm going to give that one to the radio signals detected from space, which unfortunately for all of the expert radio astronomers here means that you guys are wrong by a couple of years on this one. That's all right. It means there's knowledge to be gained when we're wrong, right? So in 1930 is when AM station car radios began being placed in cars. FM radio stations started coming around in 1952. So Carl Jansky accidentally detected radio light in 1932 and thus began the field of radio astronomy. All right, you guys are 0 for 1, which means you need at least 3 right. I've been having babies on the brain lately, and so question for you is, which is longer? The wavelength of radio light in the middle of the FM dial, so let's say you're turning it to 98.5 megahertz. What's the wavelength of that light compared to the length of the average newborn, such as little Buzz Lightyear right there? Hopefully not Buzz Lightyear, but little Buzz Lightyear right there. I'll give you guys like 30 seconds or so for this one. All right, time's winding up. Get your answers locked in here. Who here thinks the answer to this one, and you actually would have gotten the answer to this one if you were listening very intently to Chris's talk, so not to put Chris on the spot, but we'll see here. Who here thinks the answer to this one is the wavelength of radio light in the middle of the FM dial? What about the length of the average newborn baby? All right, Well, I'm giving that one to the length of the average newborn baby. Do we have any sense from the live stream what they're thinking? If they're going one way or another, not got a sense for that one. That's all right if we don't got a sense for that one. Yeah. Unfortunately for you guys, the answer to this one is the wavelength of light in the middle of the FM dial. And in fact, the answer to this one, you might have asked yourselves, why do you got that weird looking radio antenna on your old school cars? Well, it's because I needed to move an electron about that much distance to be able to observe that radio light. Unfortunately, teeny tiny cute babies are a little bit smaller than that. Even the long, not cute babies are smaller than that as well. All right, what is larger between these two? So you're over 2, you need the next 3 right. Is it the surface area of the radio quiet zone, of which 9th Street is the edge of the radio quiet zone, centered around Green Bank, West Virginia, or the surface area of Pluto? I'll give you guys about 30 seconds for this one. My dad thinks Pluto, but what does he know? He's not an astronomer. Yeah. I gave you what the picture of the spider was. All right. Time's up for this one. Say it again. They're going Pluto. Live stream's going for Pluto for this one. Okay. They'll be the tiebreaker on this one if we need it. All right. What is larger? Who here thinks the surface area of the radio quiet zone? More like the clap quiet zone, am I right? What about the surface area of Pluto? Who thinks that one? It would be awesome for the few people if it was the radio quiet zone, but it is the surface area of Pluto for this one. So round of applause for all of you guys. We got 1 right. We need the next 2 right. All right, question number 4. What has a larger angular size? Did I put the grain of rice here? I forgot the grain of rice. That's all right. Between these 2 things, the Milky Way's supermassive black hole, located 25,000 light years away and is imaged by the Event Horizons telescope, or a grain of rice held by me up the front, about 20 yards away. Which of those 2 things would appear bigger to your eye if you could see both of them? I'll give you guys like 30 seconds or so for this one before you get your answer in here. All right, let's get this locked in. Who here thinks the answer to this one of which one has a larger angular size so it would appear bigger is the Milky Way's supermassive black hole located 25,000 light years away? Ooh, you guys better be right for this one. Otherwise we got lots of, and I got some students here as well, so they better be right as well. How about a grain of rice held by Buzz Lightyear up the front? Yeah, okay, you guys got this one right. I couldn't trick you on this one. In fact, it's about 2 million times bigger. If I wanted my grain of rice to be the same angular size of that black hole, I'd have to go about halfway to the distance between the Earth and the Moon. So how big is that angular size? Imagine a donut on the Moon. That's the angular size that the Event Horizons telescope can observe. Absolutely mind-boggling what we can do with radio astronomy. Last question, if you guys get this one correct, or if you get it wrong, you get the prizes up the front. And so which of the following weighs more? Is it the Green Bank telescope or the combined weight of all the buildings at UVA? I'll give you guys 30 seconds or so for this one. We'll say it's not counting the cranes for this, so don't count the cranes on campus for this one. All right, which way are we leaning for the live stream? We got to guess one way or another here. They're going towards 2. Okay. All right, so who here thinks the answer to this one is the Green Bank telescope? Yeah, come on. Be your own person. Come on, do what you got to do. Well, what if someone was standing on it, right? What about the combined weight of all the buildings at UVA? Yeah, radio telescopes are big, but they're not that big, guys. So yeah, I did not even calculate the answer for this one. It's way more than 7 million pounds for that one. It's big. It's big. It really is big, and you should go see it. But it's nowhere close to the weight of all the buildings at UVA. That means you guys went 3 for 2. Unbelievable comeback. They're already writing songs about it. Means you guys during the intermission are going to win the mini prizes up the front. So round of applause to all of you guys for that. All right. So what we're going to be doing now is we are going to be transitioning to our second talk of the night. And the second talk of the night is going to be by a postdoctoral researcher at UVA. So Ashish Gupta, a postdoc at UVA. He studies star and planet formation and specifically the interaction between planet-forming disks in their environments. Okay? It's going to take me a moment to get Ashish's talk set up, but round of applause for him before he gets going with this talk.
Hello.
Okay, that's always an awkward transition, and so to not make it awkward for Ashish, let's give another round of applause before he begins this talk. Clicker right here, and then down to proceed forward. Okay.
Thank you for 2 rounds of applause. As the slide says, I'm Ashish. I'm a postdoc at University of Virginia. Usually people don't know what a postdoc is. It's something after you finish your PhD and you still don't have a permanent contract, like you're not a professor. So it's sort of like a transition job. And I'm going to talk about how to make a planet. Please don't try this at homes. That's good. So why do we care about planets? Because we happen to be living on one. And Earth is not just the only planet in solar system. There are many planets, Uranus, Neptune, Saturn with the rings, Jupiter. There's the sun in the middle. The video looked better in my laptop. There's Earth, Mars, Venus, Mercury. So the point I want to make is that there are 8 planets in our solar system, right? And they're so different from each other. Their distance from the sun is very different, their sizes are very different, and so on, right? And thankfully, we are on the one planet which is habitable and suitable for life. Yeah. Okay. Yeah. An exciting thing which happened in last few decades is now we can also detect planets around other stars, not just around our sun. Some of these planets we can just directly see. So this is a planet going around the star. The starlight has been blocked, so we can see the light from planets. But this direct imaging we can just do for really bright and really big planets. Most of the planets we find in an indirect way like this. We keep seeing the light from the star, and when the planet passes in front of the star, the light decreases a bit, and that's how we can infer that there is a planet around the star. So we have played this game and similar games, and now we have more than 5,000 planets around other stars discovered. So in this image, the x-axis is how far the planet is from their star. So these are solar system planets. Mercury is the closest planet to the sun. Neptune is the furthest planet from the sun. Earth is somewhere in between, and these are the planets which we have discovered so far. Similarly, this is how big the planet is. Again, Mercury is the smallest planet. Jupiter is the biggest planet in solar system. Earth somewhere in between on the smaller side. And these are the planets which we discovered. And based on how big the planet is and how far the planet is, we can tell something about what kind of planet it will be, right? So if it's, let's say, a smallish planet at similar distance from the star like Earth is, it's going to be rocky like Earth. But if a similar planet is closer to the star, it's going to be very hot. So all the rock will be molten into lava. If it's slightly bigger planet, it may have more like thicker oceans and ices. If it's bigger and as far from the star like Jupiter is, it's going to be something called cold gas giants, which is it's a giant and it's cold because it's far from the star. But if it's close to the star, it's going to be something which we call hot Jupiters. So based on how big and how far the planet is, we can tell what kind of planet it is. And one thing you can notice in this figure is that we don't find many planets in this area. Can anybody guess why? This is not part of the official trivia.
They're too hard to see.
Yeah, exactly. So they are too hard to see. Because if a planet is too far from the star or too small, it's just harder to find. But astronomers and engineers, we are working on making next generation of telescopes so that we can push this boundary more in that corner and we can try to find Earth-like planets around sun-like stars. Okay, so this was the topic of my talk. How do these planets form with all their diversity? And also, like, planets seem to be quite common. So this is a process which should happen often. I hope you have seen one of these. These are clouds on our Earth. And there happen to be similar clouds within our galaxies. Maybe you have seen one of these beautiful images. Now, what happens in the clouds on our Earth? There are some overdensities which collapse to form raindrops. And often raindrops, they don't form, it's not just one drop, it forms in a group, which we call rain. Similarly, there are overdensities in these clouds in the galaxy, which collapse under their gravity to form stars. And like raindrops, usually stars also form in groups. So now I'm going to show a numerical simulation. So what it is that somebody put a bunch of equations in a supercomputer. They tried to, because humans live very short compared to how these star forming timescales are. So we cannot really see the whole process of star forming. And the timescales of PhDs are even smaller. So what people usually do, we rely on numerical simulations in which we input all the physics which we know, and we let a supercomputer run a mini universe, sort of. And then we can learn something from that simulation about the reality. So here the bright regions is basically where the dense gas is. And you can see that the gas is moving because of its gravity. It also looks better in my laptop. And then there are dense regions which start to form stars. Once the gas is dense enough, it starts nuclear reactions and the star is formed. And then you will see a burst of stars forming around here. All right. Now let's look at what happens around each of these star forming. So this is exact same simulation, just focused on each of these stars. Whenever new panel appears, it means a star has formed, and then you will see what's happening around these new stars which are forming. So one thing you will see is that all these stars, they end up forming a disk of material around them. There are some binary systems which are interacting with each other. Some systems are more chaotic, some are more chill. Some of these stars, they have already left their cloud, so you don't see any stuff around them. But you see that almost every star forms a disk of material. And it's the reason more or less is the same reason why a ballet dancer or an ice skater starts rotating faster if they bring their hands closer. It's angular momentum conservation. It's basically that rotation starts becoming more important when something decreases in size and has some initial rotation. So because of this rotation, there's a disk of material around these baby stars. So this is how we, So this is how we think of star and planet formation. That there's a dense blob of gas which forms stars, and there's stuff falling. And then there's a stage where there's a star in the center and a disk of material around it. And we think this disk of material forms planetary systems like our solar system. That is why solar system is on a plane. It's not randomly oriented because it formed out of a disk around baby sun. Okay, thanks to the last speaker, I don't have to talk much about this. But can we see disks? Not in visible wavelength, sorry. But we have to go more towards radio because these are very cold sources. ALMA, which was also mentioned in the last talk, which is my favorite telescope because that allowed me to do my PhD thesis. It's a radio telescope in northern Chile. National Radio Astronomical Observatory at Charlottesville has played a huge role in making ALMA possible and in continued development of ALMA. There are like 60 antennas. Each antenna is 12 meters. I think it's about 36 feet. Somebody can correct me. Here's a human for scale of how big the antenna is. This is the human. So we do observe these disks now, right? And this is what we see with ALMA. And you can see all these disks, they have like these gaps and rings. And we think a lot of these gaps and rings are formed by planets, baby planets within these disks. So baby planets, they're going around eating away the material of the disk, and that's why we see these gaps. Okay, so now we know that there are disks where probably planets form, but how do planets actually form? What these disks start with are dust particles, which can be quite small. So for example, hello, yeah. Something much smaller than the width of our hair, right? To grow something from this to something like Jupiter, which is huge, which is, I think it's like 10 Earth side by side, just for the diameter. How do you do this? So there's no one answer. It's a multi-scale process, and you gradually add up bigger and bigger chunk of dust to form planets. So first you start by converting these dust to something called pebble size, so something which maybe you can hold in your hands. And this you can do by just sticking good old collisions, and they stick together. And these are actual experiments done in Germany, where there is a huge tower and people drop stuff, so you can see how interactions happen in low gravity. But you cannot keep doing this forever, because once the particles are big enough, yeah, so you can only play this game up to a point when you till you form this pebble size, and then you have to grow this pebble size particle to asteroid size particles, and this is somewhat magical. We call it streaming instability, and I will not go at all into the theory of this, but it's basically a consequence of dust moving within the gas. So here, the brighter, the yellow-green regions show where the dust is coagulating, is like collecting within the gas as it moves within the gas. And you will see that the dust starts forming these clumps, right? And then these clumps basically collapse to form asteroid-sized particles from pebbles. And one analogy, so these are asteroid. One analogy I think of is just like when you put some chocolate powder and your milk is not hot enough, and then you have this clumpiness. It's basically a consequence of how the powder is moving within the milk, right? It's not a very good video. Okay, so now we have these asteroid-sized things, and we want to make them still bigger to form planets like Jupiter. And once you reach asteroid size, the objects are big enough that their gravity becomes important. So gravity was discovered by Newton when an apple fell on him. Probably not the same apple, but I wasn't there. So the thing about gravity is that the more massive you are, the bigger your gravity is, right? So once you grow big enough to be asteroid size, you can have gravity, which you can just bring material in. So you have asteroids moving in these disks, and they keep feeding material because of the gravity, like a vacuum cleaner in the disk, and start growing like planets. So this is just an artistic impression. It's not a simulation of showing how planets eat up material in the disk and grow. So there's a disk, and there are some big chunks of rocks which aspire to be planets. And then they eat up all the material around them. And eventually, most of the disk either falls onto the star or falls onto these planets, and very little is left, and it can just be cleared away by the radiation from the star itself. And then you have planetary systems like our solar system. Okay, the really exciting thing which happened in last few years is now we actually see planets forming. So this is a famous source, PDS 70. So there's a disk, and here there's a planet forming, and this is material around planet. And the idea is that probably in this material around planets, moons may form. So now we are pushing towards finding and more planets forming within these disks. A bit about my research. It's just one slide. So what I study is interaction between these disks and their environments. So our field used to think of disks as clean, isolated systems which form planetary systems. But they're still moving in the clouds, like I showed earlier, right? And it could be that the disk is moving, and there's a chunk of cloud which comes close enough to be attracted by gravity and falls onto the disk. And this can add more material, so you can form bigger planets, and it can bring something which is chemically different, and so on. So it can do all sorts of weird things to the disks. So I use ALMA mostly to study this. So there are these disks in the center. There are two disks here, and I study how material falls onto them, how often this happens, and what it can affect, how it can affect disks and planet formation. Okay, that's it. To conclude, planets form in disks of gas and dust around young stars. And it's not a single process, it's a group of processes which grow tiny dust grains into giant planets. So that's it. Thank you.
All right, we got time for a couple of questions right at the front. Ashish, if you don't mind, for the billions of people watching, if you could repeat the question. Thanks.
So I have two questions. Can I ask them both, and you can choose to just answer one? One is, what makes them get round? And the other is, how long does it take?
Can I choose the second question? So yeah, so the two questions is, how do planets end up being round? And second question is, how long does it take to form them? So the planets are round mostly because of the gravity, because gravity is the kind of source, if it's small enough scale, tend to bring everything spherically close in. And how long it takes, it's a good question. So rough idea is million years, more or less, but there are people who would want planets to form faster, because as you can see, the disks start losing material, right? So it's harder to form planets the longer you wait, because then there will not be enough stuff around to form planets. So some people want to form planets sooner because there's more stuff around. But the sooner you form, the disks are more chaotic because material is falling in and so on. So it's harder to collect dust to form bigger things. So let's say the census is around somewhere a million years.
Good question in the back. Yeah. We got time for maybe two more questions.
My question is it more common for moons to form in a protoplanetary disk, or to be broken off of a form?
Yeah, so the question is it more common for moons to be formed in the disk or later, right? So most of the moons in solar system, as far as I'm aware of, have been formed later. Like the rings, or like the disk around Saturn was formed later. Because once we lose the disk and we have planets more or less formed, it's still not like smooth ride from like there, because there's still a lot of rocks and asteroids in the disk which keep colliding into each other. So what usually happens is there is a collision onto one planet, and then a bunch of stuff gets out which appears as moon. Like that's sort of what happened for Earth. I do think that there should be still some moons which are primordial in that sense, that they formed within the disk. I'm not sure if somebody has claimed any moon to be one of those. That's a good question. Thank you.
I got one more question from the bar over here. Give some love to the bar.
So our powers of observation are getting better, but as a part of that, have we seen any observations that have bucked the theory of what we expect about how planets should form?
So the question is, our observations are getting better, but are there any observations which challenge the theory? Was that the question?
Yeah.
Yeah. I mean, to me, sorry. So to me, these are the kind of observations which challenge the theory, because from theory point of view, people like clean, isolated disks, because then it's easier, it's less chaotic, so it's easier to form planets. But now our observations are showing that disks are not clean and isolated as we thought. We think that, as usually is the case with science, it's always more complicated than we expect. And we think that they are continuously interacting with the clouds around them, with the other stars forming around them. And there are also some massive stars nearby, which is boiling these disks. So that's one of the way in which observations have challenged our theory. But there are also many ways. Another way observations have challenged the theory is that the disks do not seem to be massive enough to form planets. Like we expected this to have more stuff, but they don't have as much stuff. So one idea which I like is that there's more stuff coming in the disks, which can explain that gap between planets and disks. So yeah, there are many observations bring many challenges.
All right, let's give Ashish another round of applause. One of the things that I want to emphasize too is, one of the things I want to emphasize, I'm sure a bunch of other hands for people with questions. During the intermission, please feel free to take advantage of the fact that you're drinking and being merry with a bunch of professional astronomers as well, right? And so come up, ask us questions, ask Ashish, Chris questions, ask Anna questions as you have them as well, as we transition after the trivia to the intermission, okay? So what we're going to be doing now is we are going to be transitioning to our main trivia game, and that's going to be the one that makes use of those sheets that my wife passed around for all of you guys. And so make sure to get those up, at the very least those of you guys that want to play along with the trivia. And what we're going to do is I'm going to come back to this QR code, but I'm going to quickly go through all the questions together. You don't need to answer the questions at the rate that I'm going through them, because I'm going to let this cycle for about 10 minutes as you guys get more drinks, or maybe step outside to go check out the stars or something. But if anybody needs a trivia sheet, please raise your hand, and my wife will come walking around. Well, she'll be wobbling around at this point, but she'll be walking around to hand you guys some of those, or maybe you can come up to the front as well, and that'd be appreciated. Okay, so question number one, and again, we're going to come back to that QR code after all I cycle through all the questions. Question number one. The word radio originates from the Latin word radius, meaning ray or beam of light, but this wasn't the original name for radio waves. When these waves of light were initially discovered in the late 1800s, what were they called? Were they called sonic waves, Hertzian waves, magnetic waves, Planck waves, or energy waves? Question number two. At the end of a massive star's life, it collapses down to a rapidly spinning object known as a neutron star. The first detection of these objects was observed in 1967 by graduate student Jocelyn Bell Burnell when she observed pulsed radio light from them every 1.3373 seconds. Yeah, pulsars. What were these objects originally jokingly called by the discoverers? Were they merry-go-rounds, lighthouses only in space, or LOIS, little green men, or LGMs, some terrible electronics mistake, or STEM, or gnarly American government secrets, or NAGs? Question number three. Based on appearance alone, which of the following main sequence stars is the most massive? Our last talk of the night is going to talk about massive stars, but you guys got to get the answers in before that talk begins. So hopefully you guys can figure this one out. Question number four. Algol is a famous star in the constellation of Perseus that visually appears to dim for about 10 hours every 2.87 days. What mechanism do astronomers now suspect causes the periodic dimming of Algol? Is it that a large planet blocks the light from Algol? Is it that Algol physically grows or shrinks in size? Is it just an optical illusion caused by the Milky Way? Is it a multi-star system where a dimmer star occasionally passes in front of a brighter one? Or, as the ancient Greeks thought, is it the demon eye of the Gorgon Medusa occasionally winking at the Earth, as held by the hero Perseus? Question number 5. All but one of the following are the names used for planets discovered in other solar systems. Which one is made up? Is it cold Venus, hot Jupiter, mini Neptune, super Earth, or are they all used to describe other planets? Oh, whoops, I accidentally put up the thing that's asking for you guys to donate some money, so apologies for that. But if you do have the ability to do so, we'd appreciate some as you guys come up to the front to grab your mini prizes during the intermission. Apologies for that. Question number 6. All of the following are true. Which gives us the highest confidence that planets formed out of a rotating cloud of gas and dust? Is it that there are 4 rocky and 4 gaseous planets? Sorry, Pluto. Is it that Jupiter has the largest moon in the solar system? Is it that all the planets revolve in the same direction and in a plane? Is it that all gaseous planets have rings? Or is it that the sun rotates once every 25 days, depending on which part of it you're looking at? Question number 7, which is our Facebook trivia hint. You're still welcome to join, go to our Facebook page if you want, and please don't Google any of the other questions, just to be clear. But if you follow us on Facebook, this should help you out at the very least with this question. And it has to do a little bit with my hat. I'm wearing my Shire hat tonight. In Lord of the Rings, the Star of Arendelle is the light that shines in the horizon, both in the morning and the evening. It consists in a boat raised by the Valar and led by Arendelle, who carries a shining Silmaril while watching the doors of the night. What? What is the real astronomical object that inspired the Star of Arendelle? Is it the planet Venus, the crescent moon, Sirius the dog star, the Milky Way, or the Aurora Borealis? Question number 8. Simple one for this one. Has to do a little bit with the name of my cat, who my wife named after Major Tom. But how far away from Earth does Major Tom get in David Bowie's Space Oddity? Is it about 1,000 miles, about 100,000 miles, about 10 million miles, billions and billions of miles, or is it never actually stated in the song? Question number 9. The painting to the right depicts an astronomer sitting in front of a celestial globe with an opened book in front of him. It was completed in 1668 by Dutch Golden Age painter Johannes Vermeer, and this painting currently hangs in the Louvre. What is its name? Is it Touching the Heavens, The Astronomer, Reflections on Science, Pursuing Wonder, or Pryal Poetically Ponders? Who's that Pryal guy? Buzz Lightyear Poetically Ponders, am I right? Question number 10. Have you guys been looking up? If not, you can step outside to look up for this question. But all but one of the following objects have been visible to the naked eye at the beginning of astronomical twilight this past week. Which one has not been visible? Is it the Pleiades, Jupiter, Orion the Hunter, Mercury, or the Big Dipper? So I'm going to go back to that QR code for those of you guys that want to scan it. You're going to chat with your neighbors for this one if you'd like. And then at the end of our intermission, you're going to turn that in to my wife up the front. Now, again, you guys got more questions right than wrong for our radio, which means you've won some of these mini prizes up the front. I encourage you to come up to the front and get some of those mini prizes. And we'll go through about 7 minutes or so of intermission. Go get a drink. You guys can turn on the music from Firefly. We'll come back together in about 7 minutes or so for the last trivia game.
that the Very Large Array has a membership program? Hi, my name's Cypress, and I'm the membership coordinator for the Very Large Array. Here's why you should become a member. The new VLA membership program supports STEM education and building the Next Generation Learning Center here at the VLA. Become a member today and inspire the next generation.
Know this one. It's something that we call grab bag trivia. And the way grab bag trivia works is that I have 5 different categories of trivia questions that I'm going to ask people to try to answer, and just sort of firsthand that I see, if you know the answer, you guys can win some of the larger prizes that we have up the front as well. And also, I guess if anybody from Firefly is listening, if you can cut the music, that would be great. But our first grab bag trivia question for tonight is a game called Astronomical Alignment. The way that astronomical alignment works, I'm going to show you guys 3 related words, clues, images potentially. You guys just need to guess the connecting concept, category, or word for those 3 words. All right? And so the words for our astronomical alignment for tonight, and again, just by raising your hands, we'll see who has the best guess for this one, are the words chocolate, war, and Tuesday. What is that connecting astronomical alignment?
Mars.
Got a guess here? Up the front, we got a guess. The guess is Mars, and Mars is the right answer for this one. We are a family, so please, if you wouldn't mind celebrating your family member for getting this answer right. The answer to this one is Mars. Mars, of course, Mars bars. The god of war is the god Mars. And then Tuesday, each of the days of the week is named after a planet. Tuesday, Martes, is named after Mars's day. Today is the moon's day, or Monday, right? So awesome, we got that one. Next one is astronomy anagrams. I scrambled up some astronomical word. You guys just got to figure out what that astronomical word is. And it looks something originally like this. Well, I didn't see any hands over here. Yeah, right here. Microwave, the first person to raise their hand and get this one right. Yeah, round of applause. Microwave's the right answer for this one. I didn't even have to go through the simple one, so that was a lot easier. Microwave, it's a type of radio light as well, and so please make sure to wait till your microwave ends before you open it up to get your food so you don't create any radio interference. No, it's not that big of a deal, but it is a big deal if you're close to Green Bay. Photo pixelation, I've pixelated a photo, some astronomical photo, something to do with astronomy on tap or astronomy. You guys just got to figure out what that photo is, and it looks a little something like this. Right here? That is the GBT. Yes, I thought we were going to go a couple of ones for this one. I thought this was going to be the one that clarified it for everybody. This is the GBT. The GBT is the Green Bank telescope. Green Bank telescope, that's that radio telescope. That's basically one of the largest movable objects. Question number 4. It's everybody's favorite game. Help me out with this one. It's Name That Star. I genuinely, that's one of the things I love the most when that actually works. Name that star, that's right. Name that star, how's it work? I'm going to have you guys try to guess some star with some clues. The first clue is that it looks like this. Can you name that star? Yeah? Sirius is not the right answer for this one. Yeah. I'll take one more guess in this Name the Star round. Say it again? Procyon, no, or Rigel, no for this one as well. So let's hold some of those guesses. So it looks like that, which means you guys know a lot of information already. Its name actually comes from the Latin meaning female warrior. Anybody been practicing their Latin lately? So any guesses here? In the back, yeah? Alpha Centauri is a good guess. That's not the right answer for this one, though. Not Alpha Centauri. Any other guesses? Someone said Athena? Not Athena. All right, I'll clarify it a little bit. It is the 3rd brightest star in its constellation and the 25th brightest star in the sky. Surely you guys know your bright stars. This is the 25th brightest star in the sky. Astronomically important for humans for hundreds of thousands of years. One more guess in the back, yeah? Say it louder. The North Star is a good guess, but not the North Star for this one either, yeah. North Star is not as bright as this one, actually, believe it or not. Any other guesses? Okay, let's do our last clue. It's the inspiration for a name of a famous character in the Harry Potter series. Yeah? It is not Regulus, unfortunately, for this one. Yeah? Bellatrix is the right answer for this one. This is the star Bellatrix. Bellatrix is the other shoulder of Orion. In fact, most of the Black family in Harry Potter is named after famous stars. Sirius Black, for example. Regulus is another one of those. All right, last round. This is Emoji Decoder. Not a new game anymore, but a favorite game nonetheless. You guys have to figure out the phrase, movie, or historical event or concept expressed with emojis. The emojis are these. Anybody know what that astronomical connection is? Yeah. It is not Interstellar. Good guess for this one, though. Not Interstellar. Any other guessers? I'll give a hint in just a moment. Let me see in the back. Yeah? The International Space Station is correct for this one. That is right. Don't even have to give my hints. That's the UN flag, a star, a station right there. And then, of course, we have a satellite. It's the International Space Station. Round of applause for everybody that won our prizes for this one. All right, guys, so what we're going to do now, me and my wife are going to grade through the main trivia, but we're going to transition to our last talk of the night. And the last talk for the night is going to be by a graduate student at UVA. And so Anna Dignan is a second-year grad student, and she specifically studies massive star formation. So Chris studied massive star formation inside the Milky Way. Anna studies massive star formation outside the Milky Way, but also using radio telescopes and other telescopes like that. Before UVA, though, she had a postbac at NRAO, and before that, studied galaxy mergers at the Rochester Institute of Technology. So let's give a round of applause for Anna while I get her talk started.
Okay, hello? Okay, that works. Okay, cool. Okay, yeah, so thank you for the introduction, Matt. So tonight I'm going to be talking about orienting myself here. Tonight I'm going to be talking about massive stars across the electromagnetic spectrum, or a cosmic broadcast. There we go. So I'm just going to give a brief overview of tonight's talk. So first I'm going to give some science background, which has actually been covered very well by Chris and Ashish, so thank you to them. But I'll talk about massive stars, how do we define one, and why do we care about studying them, and briefly remind us about the electromagnetic spectrum. And then I'm going to take you on a tour across the electromagnetic spectrum. We're going to look at massive star formation at different parts of the spectrum. And then lastly, I'm going to tie it to my research, so what I do as a grad student at UVA and what I've found so far. So a massive star is defined as anything greater than 8 solar masses or 8 times the sun's mass. And they're made up of molecular clouds, and these clouds are made up of mostly molecular hydrogen and carbon monoxide. And remember that because it will come back later. And they also emit light across the entire electromagnetic spectrum, which is nice for me because then I can see them at a lot of different wavelengths. And most importantly, we care about them because they are essential for the formation and evolution of planetary systems and galaxies, because planets form around a star and galaxies are made up of stars. So if we don't have massive stars, we don't have all of those things. So first I'm going to start in the Milky Way. So in the back we see Sagittarius B2, and this is a region in our galaxy where massive stars are forming. And this is great if we want to see a close-up look of what's going on and we get a really high-res image and we get to know all the details. But naturally, we ask eventually, what about other galaxies? As we can see, galaxies come in all shapes and sizes. We have some galaxies by themselves. We have some galaxies with partners. We have some galaxies that are on their side compared to us. We have some galaxies that are face on. So there's a lot of different environments and conditions. So what does massive star formation look like in these environments? Is it the same? Is it different? And furthermore, we can ask ourselves, what about different wavelengths? So this is the equivalent of, like tuning into a different radio station, and what will the music sound like on those channels? What genre will it be? So in the back, this is the same region, Sag B2, in our Milky Way, but now we're viewing it in the near infrared instead of the mid infrared. So it looks very different, and there are some similarities, and so we want to ask ourselves, where do these differences and similarities come from? So I'm going to gloss over this. This is the electromagnetic spectrum. As we go from left to right, we get shorter in wavelength and higher in frequency and also higher in energy. And along the top, we have radio and microwave light, which we should be familiar with from everyday life, such as car radios and microwaves in our kitchen. And then we have infrared light, which we can think of as thermal or heat light. And then we have visible light, which most of us see. And then we have, well, not everyone. And then we have ultraviolet radiation, which we're familiar with, which is why we need to put on sunscreen, because it's bad for your skin. And X-rays we know from the dentist's office or TSA. And gamma rays, Chris took my joke, but these turn you into the Hulk, so they're bad. Oops, sorry. So I'm going to be talking about 3 of these regimes tonight, radio, infrared, and visible. So here we go. I'm going to start with radio frequencies. So right now we're looking at the center of our Milky Way in radio light, and it looks very cool. There's a lot going on. And tonight I'm only going to talk about 3 ways to generate this radio light. So the first way is through supernova remnants, and this is the synchrotron emission that was discussed earlier tonight. So just to review, when a massive star dies, it first collapses in on itself and then sheds its layers, and they go flying off into space, and we call this going supernova. And then their remnants stick around, and these leftovers have magnetic fields, and if an electron floating around gets caught in the magnetic field, it gets sped up. And this change in speed is what generates light at frequencies like 3 gigahertz, and this is called synchrotron radiation. And as I go through the spectrum, I'm going to be showing the same galaxy, one that I study myself, at the different wavelengths. So this is NGC 4321, and we're seeing the synchrotron radiation. And then the second way to get radio light is through massive stars when they're still alive before they go supernova. And so the light that these massive stars emit during their lifetimes is strong enough that it strips the nearby gas of its electrons. So this is the thermal radiation that was discussed earlier. So the free electrons are free to move around, and if they get close to an ion, which is a molecule or atom also missing some electrons, it'll get a little speed boost. And change in speed gives us light, this time at slightly higher frequencies, around 33 gigahertz. And we call this free radiation because the electron is free both before and after it interacts with the ion. And so this is our friend, NGC 4321, and now we're seeing the free radiation. So you can see that it looks pretty similar, but not the same. And so the last way I'm going to talk about to get radio light is a little more complicated, so bear with me, please. So we're going to talk about the rotational transition of carbon monoxide. Thank you. So CO can be excited to a higher rotational energy state, and we do this by changing its angular momentum. Don't know if the GIF is going to play. That is unfortunate. It is not going to play. Just imagine that the molecule is spinning around, but then it slows down, kind of like a figure skater when they move their arms, like Ashish was talking about. Yeah, there you go. Thank you, Matt. And how do we get this change in angular momentum in the first place? Well, we collide with other nearby particles, like the molecular hydrogen, which I mentioned. These two gases exist near each other. And so when CO falls back to a lower energy state, then that is when we get the emitted light. And specifically, this is the 2-to-1 transition, so the second rotational energy level to the first. And this specifically emits light at 230 gigahertz. So now we're really getting up there in the radio regime. And this is, again, 4321, now in CO 2-to-1. And now we're going to, actually a little more on CO. So why do we care about CO? Because the first two ways we talked about involve molecular hydrogen. So why are we suddenly talking about CO? Well, because we can't measure molecular hydrogen the way we can with CO with the rotational transitions, because molecular hydrogen doesn't have rotational transitions the way CO does, based on some chemistry stuff that I won't get into right now. So we can use CO instead because it is relatively as common as molecular hydrogen, not perfectly, but mostly. And we can observe it, as I just discussed. So we can use it to trace the molecular hydrogen. Okay, so now we're going to move on to infrared frequencies or wavelengths. And so this is, again, the Milky Way center now in infrared light. And this light is coming from dust around stars. And the dust absorbs starlight, and it gets heated up, and then it re-radiates this heat, and that's what we see in the infrared. And now I'm going to switch from talking about frequencies to wavelength, because that is what is commonly done in astronomy. So this is a wavelength of 21 microns, and this is our friend NGC 4321. And now we're going to talk about visible light and ignore the Earth in the background. So this is still the Milky Way in now invisible light. Hello? Okay. And I specifically studied the visible light from hydrogen atoms when they fall from a higher to lower energy state. And you may think, wait, isn't that what CO does? This is slightly different. So now, instead of a rotational energy state, we're talking about an orbital energy state. So if you remember from chemistry class, and we have these electrons existing in like clouds or rings around atoms and molecules, that's what we're talking about. So again, the emission is generated when it falls back to a lower energy level. And it's excited in the first place by a starlight that excites the hydrogen gas. And when we go from the third to second energy level, we get light at a very specific wavelength of 656.3 nanometers. And this is very specifically called H alpha, because hydrogen has a lot of transitions. So this is NGC 4321, and now invisible light. Oops. So we need to listen to all of these different frequencies, wavelengths, channels to get the full song of massive star formation. That is kind of corny, but that's the truth. So the reasons we have to, besides they look different and that's cool, is synchrotron emission traces the end of massive stars, the final stages of the life cycle, whereas other tracers like free emission trace massive stars when they're still alive. So we get differences naturally, and that can affect our estimates of massive star formation rates, so we want to take that into account. And another thing we have to consider is some of these wavelengths can be affected by things like interstellar dust. So visible light can be absorbed by space dust in between us and what we're looking at. And to the right is just an example of that. And you're literally missing light from these massive stars. And so that affects your massive star formation rates. They can be too low, and that's not good. So on to what I do specifically as a grad student. I look at multi-wavelength data for a bunch of nearby galaxies to estimate the rates of massive star formation in various parts of these galaxies. So here's a little summary slide. So we've talked about some of these telescopes as well. So we have the VLA, which is where I got my free and synchrotron emission data. And then we have ALMA, which is how I got my CO data. And then we have James Webb, which is how I got the infrared data. And it looks very small in person, isn't that weird? And then finally we have MUSE, which is an instrument on the Very Large Telescope, I think also in Chile, and that's where I got my optical data from. So the other cool thing about my research is that it covers a lot of different galaxy types or appearances, or as we call it, morphologies. And this can tell us how different things in different galaxies affect star formation rates. So things like active black holes or merging galaxies or starburst rings, so these rings of elevated massive star formation. And here are just some galaxies in my sample that are examples of these really cool features. You can't really see the AGN, but it's there. And then the interacting systems, we can see that. And the starburst ring, we can see that as well in infrared, which is really cool. So on to more specifics about my research. So one of the science questions I'm trying to answer is, how does turbulence in molecular gas from exploding stars potentially prevent it from collapsing and forming new stars? So again, when a massive star dies, it goes supernova, and this is an explosion, and it injects a lot of stirring up or turbulence in molecular gas. And we can wonder, well, is the gas then too turbulent and moving around too much for it to condense and form new stars? And so I've started working on this by measuring the amount of turbulence and comparing it to the strength of the synchrotron emission, with the thought being the weaker your synchrotron emission, the older your supernova remnant, and the more time it has had to propagate in outer space and stir up the gas. So this is what we see so far, except for a few outliers, and maybe these outliers are because of those different features in those galaxies. So again, things like active black holes or elevated star formation for reasons we don't know yet, or that they're mergers potentially. And my next step in this project is to study how star formation efficiencies correspond to supernova activity. And so I mentioned earlier that CO is a tracer of molecular hydrogen, but it's not perfect. So there is a conversion factor or a ratio that I have to determine, and we can make it as complicated as we want. So this is the next thing I have to look forward to. And then the next question I'm trying to address is, do infrared and radio star formation rates agree? And if they don't agree, why? because it has been shown before that some of them don't follow that one-to-one line. And for the ones where we have an elevated infrared star formation rate, it has been theorized that this is because the infrared light is tracing both massive and non-massive stars, that it doesn't discriminate. It just is tracing all of the stars that exist, whereas radio star formation rates are specifically for massive stars. So this difference has only been seen in 1 or 2 galaxies, so my work is pushing that to 12 galaxies and hopefully more. And for the ones that disagree in a different way, why is that? Maybe AGN, who knows? And then the next part of this project is looking at how does stellar mass or pre-existing stars impact star formation rates. So is your gas all used up and in the stars that already exist, and there's no gas to form new stars? So I'll be looking into that. And then in the more distant future, I will be looking at massive star formation rates in the early universe. So what was it like 1 billion years ago? What about 11 billion years ago? And some of this work has been done for a different study, and we can see that there are, again, similarities and differences between different wavelengths. So optical versus radio galaxies look different. And I'm going to be extending this to 100 sources. So this is going from like the 10-ish galaxies I study right now to 100, and that's very exciting. And we're going to see what star formation was like way back when the universe was younger. And I just wanted to finish by restating that. What is this?
Oh, that's the mic. That's so your parents can hear.
Oh no. Sorry, I'm breaking the mic. So I just want to summarize by saying that my research focuses on, the understanding of planets and galaxies and broadly how we got here. Because again, if we don't have stars, we don't have galaxies, we don't have planets, we don't have Earth. And also thank you to UVA for letting me go to the VLA. They do have an awesome visitor center. I got so much stuff there. So yeah, thank you for listening. I don't even know how I did that.
Yeah, you hold that lower.
Okay.
Okay, we got a couple minutes for questions. Does anybody have any questions for Anna? And just so you know, you heard earlier, you can repeat the question so that people through the live stream can hear as well. Anybody got any questions for Anna? At the front. Okay. You're very welcome. Let's just use that, actually.
Oh.
I was so curious to see how AI is helping you in your research, if it is.
Wow, that is a crazy question to ask because my advisor, Oh, sorry, the question, thank you, Kierna. The question was, how does AI help me in my research? And I was starting to say that's a great question because I am actually looking into that as well. I'm not sure yet, but there are a bunch of people at UVA and NRAO who do work on AI, specifically in astronomy, as part of Cosmic AI, which my advisor is a chair of. So I'm looking into that. I think definitely for radio versus optical morphologies, AI is good at identifying different galaxy shapes. I'd be interested more in predicting massive star formation rates, but that's a little more complicated, and I'll have to get some collaborators for that.
I was wondering, could you just chat in general about what the process is like for a graduate student to use a radio telescope, to analyze the data, to actually create new knowledge in the first place? What's it like for the people that haven't gone through grad school, which is good for you, but explain that a little bit.
So I've been fortunate enough to do this for the GBT. So the process is I did kind of the mini version of it, which is DDT, Director's Discretionary Time, You just sort of slip it in if there's scheduling time. I was re-observing one of my galaxies that we had some bad weather and it affected the observations. So I was redoing those observations, and yeah, you write a couple pages of, you know, what you want to look at, why you need to look at it, the specifics of, like, I need to look at this frequency for this long to get it to be this bright. And then hopefully someone approves it, and then it's scheduled. And I was actually at a conference when my observations were scheduled, so I maybe had a little bit of a different experience. Some people get to go to Green Bank, but I did it remotely with my observing friend, who showed me how to, you know, remotely connect to this computer that controls the telescope, and then there are a bunch of screens to, you know, move the telescope and make sure everything's okay. And then a couple weeks later, you get the data and you get to look at it and you get to say, like, oh, this actually isn't that great, or oh, this is wonderful, thank you so much. And yeah, it's fun. It's really cool to see, like, the actual process instead of just getting the data in its final form. You're like, okay, you know, yeah.
Well, we got time for one more question. If anybody's got one more. One more over here. Yeah.
Hi, thank you. So this might be a stupid question. So I'm really interested in how you're discussing turbulence. And for most turbulence that we experience on Earth, you see it in fluids, right? You see it in, like, your gas tank, or you see it in water, or you see it in the air, in the atmosphere, right? But in space, you're operating in a vacuum, right? And I was wondering if there's anything different about studying these gases in the vacuum of space that impacts your equations for how these media behave that is different from what you might see in other circumstances.
Okay, so the question was turbulence for things on Earth versus in space, and how does that affect my research? So I'm focused more on calculating the rates of massive star formation and purely observing the turbulence, but not trying to calculate it or run equations or simulations. But other people do that, and I'm not quite sure what the differences are, but in my preparation for this, I did find some really cool animations by some other astronomers of simulated turbulence, and I think there are definitely similarities there between, like, regular fluids and what we have in outer space. But this little, yeah, I don't know as much about the fluid dynamics.
All right, well, let's give another round of applause for Anna for an awesome talk. And she'll be hanging around as well if you guys have any other questions to ask. If you guys have any other questions to ask afterwards, Anna will be hanging around as well to potentially answer some of those. So what we're going to do now is we're just going to transition to the last thing of the night, which is just to reveal the trivia answers, to reveal the winners. And for those of you guys that are interested to join us up the front for some of those mini prizes, or out the back for some observing. And so I'm going to reveal the answers that we had here. You guys can see how you did for those questions. Oh no, what just happened in the back? Hopefully that wasn't, something broke, but it wasn't the Green Bank telescope, thankfully. All right, question number 1. The word radio originates from the Latin meaning ray or beam. What was the original name for it? Well, it was discovered by Heinrich Hertz, and so as a result, it was called Hertzian waves. The reason why we use the unit of frequency of the Hertz is because of that dude that helped us understand a little bit about sending radio light. Question number 2, what were neutron stars originally called? They were originally called Little Green Men, or LGMs. We quickly realized that instead it was something really cool astronomically from space. Question number 3, which of the following main sequence stars is the most massive? Well, that would be the bluest star, and the bluest star is going to be the most massive. The reddest one is the least massive. The more massive you are, the higher the temperatures your surface can get. The higher your temperatures your surface, the bluer that star looks. Question number 4, what causes the periodic dimming of Algol? Well, it's very simply that we believe it's in a multi-star system, and one of those stars is occasionally passing in front, causing the winking of the Gorgon Medusa. Question number 4. Which of the following names is made up of planets in other solar systems? Well, my research in grad school, which I'm sure all of you guys care a lot about, was about hot Jupiters. We also explored things like mini super Earths and mini Neptunes, but no cold Venuses out there. So cold Venus is the wrong answer for this one. Question number 6. Which gives us the highest confidence that planets formed out of a rotating cloud of gas and dust? Well, it's that they all, when you look at them in the sky, you can see a line. Astrologers called that line the zodiac. Astronomers call it the ecliptic. And it's because they all formed out of that plane. And we see that plane that the solar system planets formed out of. Question number 7. What is the real astronomical object that inspired the star of Arundel? Well, that was what we call the morning star or the evening star, which is the planet Venus, right there. The planet Venus, which is visible just before sunset, or just after sunset, or just before sunrise. Question number 8. How far away from Earth does Major Tom get in David Bowie's Space Odyssey? Well, that would be past 100,000 miles. Doesn't go that much further past it, the way that you work through the math, and so it's about 100,000 miles away. That's how far he gets. Not as much clapping for that one, so it seems like we did a little bit. It doesn't work with the lyrics. I've seen some people it doesn't fit the vibe of the song, but it's past 100,000 miles. Question number 9, what is the name of this image? Obviously, this one is Prial Poetically Ponders. So those of you guys okay, all right. The answer to this one is just The Astronomer. They weren't thinking too hard back then. See astronomer, call astronomer. That is exactly what they called the painting. Question number 10, those of you guys that are joining me to observe, and if you're going to do so, I'm just going to bring my telescope, which is right over there. I'm going to bring my telescope. We're going to be looking at some of these objects just outside the back here if you're interested. The objects that we're going to look at Jupiter, and we're also going to look at the Orion Nebula. So these two objects are visible. Well, the Orion Nebula is very near the Pleiades, and the Big Dipper is always visible from Charlottesville. So the wrong answer to this one was Mercury. Mercury is not visible. Okay, so round of applause to all you guys. Let's reveal the answers. So because we're not having a May Astronomy on Tap event, because of a little event that's occurring in mine and my wife's life, we decided to do 7 different winners for prizes for this one. And the first place winners got 9 out of 10 correct. So nobody went perfect 10 for 10, but 9 out of 10, there were 2 of them. There were the senior stars. So where are the senior stars? Then the back. Senior stars. Oh, some of my students. Let's go. Nice. And Star Search right up the front right here. So you guys, we'll get through what the prizes are in just a moment after I reveal what all the winners are for that one. No, that's all right. You get excited. Then the other, with 8 out of 10 correct, you guys can hang up the front. That's all right. With 8 out of 10 correct was Wiley Addyrow. Wiley Addyrow in the back over there. Yeah, a round of applause for that family. Tonka Janari. Tonka Janari, nice. And Almigos. I'm guessing it's for Alma. Almigos? Oh, Almigos right there. Nice. And then we chose 2 that just either made me laugh or made me go, oh, that's cool. But did not get as many of them right, but still win prizes nonetheless. It's the Very Large Filet. The Very Large Filet won someone prize here. And then there's very nice art that was drawn on this one. I appreciated the art, and that was very simply just by the team Raven. So Raven, if Raven is here, all of you guys that won, come up to the front, get some of the major prizes that my wife's going to help out with. Those of you guys, you won the mini prizes, you're welcome to come grab some of those mini prizes as well. And I'm going to bring my telescope out the back to start looking at Jupiter and some other objects for those of you guys that are curious. Thank you guys so much for coming. I appreciate it so much. And so thanks to Firefly as well for hosting us. I hope you guys have a nice rest of your night, and maybe I'll see you in July. Have a good one, and thanks for coming, guys. I'm going to do my telescope. You guys can hang around. Thanks so much. Yeah, I appreciate it. Yeah, we had a good time. It's cool that you do this.